All right, guys, let's go. Your lab isn't due till Monday, but Friday I might be briefing the next lab, as I warned you of. So clear the decks if you can. If you can't, well, so be it. Should have a full 2 weeks, Friday to Friday for the next lab as well. So, I mean, it's the most advanced in topic, but I don't know that it's the most time consuming. So hopefully all will be good. So we're starting the last major topic before that's covered on the second of the unit tests, which is reinforcement learning. As I said, this is learning that is specifically about taking the right action in the right circumstances. Yeah, so it's kind of like so we kind of advertised on in the first week with those cartoons of here's how agents can respond to their environment. If we're in a simulation, we expect agents that understand what's going on in the simulation and are taking a proper action. And it is capable of utility-based action selections. The one of the approaches, these approaches are very broad, mind you, broad brush in the introductory class, but it's the one of our approaches that is clearly designed to do that. And we need that for the most demanding simulation applications. We need that. Okay, so we're still kind of in ramp up mode. So, and it is Monday. So let's start out by playing a game. Okay, well, sort of a game. Kind of game my wife likes a lot. So what we have is what's called this is called the multi-armed bandit problem. It's like a casino problem. It's a bunch of slot machines. It's 3 arms you could pull. They all cost the same. You've got depending on how you phrase it, a fixed pool of money, or maybe I'm bankrolling you. You can sit there and play forever, but you're trying to maximize your return. And you start off knowing nothing. You know, there are 3 arms that you could pull. Okay, so what should I start with? Got buttons here to pull each of the 3 levers.
You gotta go lever 1.
Well, lever 1. Yeah, why not? Okay, so what you see here is I pulled the lever. I didn't get a jackpot. The stats are being accumulated here, right? Number of points 1, total reward 0. So we're 0 for 1. Pull again, go to the second lever.
Go to the second.
All right, let's try the second. Looks kind of similar to the first one so far.
You gotta go 3.
Go 3. All right. Okay. Well, I think the way you guys are rotating is kind of smart because maybe there's one lever that like always hits a certain amount, which would be a great thing to start out with. So we put 1 coin in, we get 1.5 back. So we're not ahead because we wasted 2 other coins, but
push 3 again. Yeah, push 3.
Pull 3 again. Oh, you could love to push your luck, huh? All right, let's pull it again. Hits again. All right. All right. Oh, wait a minute. Oh, wait a minute. Oh, but it still says only 2. It somehow it bounced. I faked out the brother. All right. Keep going. 3. What do you say?
Yeah, keep going.
All right.
Absolutely. Yeah.
All right. That one did not hit.
You didn't push it right. Yeah,
I didn't push it right?
Yeah, it's kind of wrong.
Since I did flub it once already. I can't say that's impossible, but I'd like to say it's impossible. All right, so now we're still positive on this machine, right? We got 1.12 coins per return. I keep going. And you're going down. Hey, maybe we were lucky. I mean, they hit a whole bunch of times at the beginning, like 3 times, but
check out number 1 or 2 again. Check 1 again. 1.
Check 1 again. All right, let's try 1.
Check 3. I know 3 was on a heater. Nothing. Man. But who knows? Maybe 1 or 2 has a massive jackpot at the beginning. Because we're getting a high percentage on number 3. But we're only at 1.5 back. What's our return here? So if every 10 pulls we win $1 million on 1 or 2, who knows?
No, so I like that reasoning. I mean, I didn't tell you anything about that there's an upper bound. I didn't say, well, nothing's going to return more than 10 or, so.
How far can we go before my wife notices how much money I'm getting?
Yeah.
There you go.
Well, with me, it's the opposite. I just see these all I see when I play these is my coins vanishing into the slot, and I don't enjoy it at all. All right. Well, let's just see. Let's try a few of these. Oh, wait. Okay, we did get it. We hit twice. It looks like two each.
Yeah.
So the jackpots are a little bigger here. We want to pull on this one a little bit.
Keep a few till you generate some.
I mean, there's nothing to say that the return is fixed either, right? It can be 2 most of the time and 2 million very rarely. Okay. All right, let's go to 2 here. Let's see if we can at least get one hit. Ooh. Okay. I don't know. So it mean with that one hit, it jumps into the lead in terms of value per play. So keep playing 2.
At least we get another hit on there. Yeah.
All right. Let's go. Ouch, 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 ouch. Takes a while. Oh, now it's back. Now it's back in the lead again.
Poster number 1.
See if we can get a different reward other than 2. No, it's 2 again. 2 again. Maybe the reward's fixed. I don't know. I coded it, but it was a decade ago. I don't know. All right. All right. So anyway, you get a feeling for what this thing can do. We have a reinforcement learning option down here, but I think I'm gonna pass on that because again, the whole point is to ramp up into reinforcement learning. We'll come back. All right. All right. So this is the kind of problem. This is a very simple problem that is in scope for reinforcement learning. Okay. Why very simple? Okay, remember like at the very beginning when we talked about vocabulary, like what makes environments hard? This is very much an episodic environment. Well, maybe. Yeah, I mean, I don't know. I guess it depends on how the slot machines are programmed. Yeah, go ahead.
Now, when we talk about reinforcement learning, we're talking about giving the machine incentives, saying, hey, plus many points if you get this type. So that a lot of wouldn't that depend on how we design this reward structure? So we said, hey, I'm going to measure you by 1 time. If you don't come back with more money than you left with, then it'll probably play 3 because there's chances of getting more money than it left, which are good.
Okay.
Now, if you say, here's 100 pulls, go maximize the value you come back with, you might get a different result.
So you like slot machines, do you?
I actually don't.
Because you're really very advanced in your thinking about slot machines. That's very appropriate. Actually, it goes beyond stuff that we're actually going to cover in the course. In the course, we're going to just kind of take one stat, which is just expected return. But that's only one possible stat. That's what you're pointing out. I mean, saying that don't come back with a loss, that's a completely different thing than maximizing your expected return.
How?
How is that a different thing? Because if I come back with $1 every time, you're happy, but I never am going to come back with $1 million. So you might be more happy with a guy who comes back with 0 100 times, but then $1 million on the 101st.
Yeah, the more money you have to play with, the more risk acceptance you can have. If that makes sense. So if you're gambling with the rent,
if you're playing the lottery and the expected value of buying a $1 ticket is $1.01, and that just means that if you buy several million tickets, you will probably get some unexpected value. As opposed to my mother-in-law who will see that and then she'll buy like 2 tickets, but I have one.
It's a ripoff. All right. So anyway, so good. So I think this gets us thinking along the right track because a lot of the issues that are there, again, this is if so my casino is not doesn't have any psychology built into the programming. It's the polls are IID polls against the distribution. So it's a completely fair thing. And therefore, this game is, back to what I was saying, an episodic game where it doesn't benefit you at all to know what happened. It doesn't, there is no second situation. There's one situation that you're in, which is I'm sitting there with a coin. Which slot should I go into? Right? And that's very different than the process of decision making on a battlefield where the first decision is, okay, we're going to try to strengthen our left flank. Okay, now what decision? Okay, well, now my left flank has been altered. We're not in the same situation as before, and we'll never get back to the original situation that we were in. And once the eggs broke, there's no putting it back together again. Okay, so this is about as easy as it gets while still being in scope for us. So that makes it a really useful first exam. Okay. Any other comments or questions about this? Okay. Let me find my slides. All right. Okay. See if I missed anything. Oh, all right. So what I'd like to do is let's see if we can generalize some principles. I think maybe we already said this stuff, but I mean, the first one maybe is too obvious. Like first, you better track returns for your arm. If you were taking it seriously and the returns weren't, your track record wasn't right in front of your face like it was in that app, you should definitely do the work yourself and track how much you're putting in, how much you're getting back, and so forth, right? That's a given, right? If we really want to do well. Okay. And the next thing, well, yeah, maybe deserves some discussion. So I'm claiming a principle here is never give up on any arm. So if we go back to our arms, right, we have, like number one, looks like a turkey. Okay. If the goal is I'm bankrolling you and it's going to be a stream of money, you're going to be playing this forever. And so you just want to maximize your return. Can you imagine, is there could there ever be a point you could imagine where you look at the stats and you're like, wait, lever one is definitely worse than the other ones. We should not invest one more dollar in lever one.
If you get down to the stuff we're doing in our statistics class of saying you get to a sufficient sample size and you say, hey, it's really unlikely that this is a lever that hits often with a good return. And I've just gotten a weird sample. Whereas our first clicks on two.
Well, but I say, there's a little bit of a conflict in our language. I said never. We decide we're not putting one more coin into lever one. And you said it's unlikely.
Well, but you come to a point where if you get sufficient data,
you can quantify the percentage of time that you're in a situation where you should continue, but you decide not. You can say like with a 99% confidence.
Yeah. So
you can't technically say zero because that's absurd.
But total aesthetics. It's a one-time.
Yeah.
So let me make sure I understand the question. Because I can say absolutely. There's a point where I would say I will never put it in, nor will I incentivize a machine to, etc.
Right. If we have, and especially if you have like a finite bankroll.
Yeah.
I mean, if I'm talking about my 100th coin, and that's all the coins I have, and I'm looking at these stats, I'm not putting it in lever one. So I've effectively completely stopped lever one. But that's not the setting here. We're gonna do this for our day job from now on, right? And the issue is that, when you go and you do those stats, right? Let's say you're estimating the return rate for lever one, right? And you start off and you have a really broad distribution around some mean return here. After a few samples, right? I mean, we'll probably get a good approximation by normal being the true underlying distribution here. And as we draw more and more, this distribution tightens up, right? And this lets you do stuff like what Nick was saying is you can look at the tail probabilities and you can put bounds on them and come up with some rational plans for that are based on that. But even after we do this like nearly forever, and this thing looks like this, it's just like a slip, but it's still a normal distribution. It still has tails that go all the way out to infinity in both directions. Right? So we don't ever get to a point where, you can be absolutely sure. Like that lever one literally could be coded. I don't know if I'd be that mean, but it could be like 1 in a million times. It gives you this amazing return.
I checked that you did not do that.
What's that?
I checked, you didn't.
I didn't do that. I didn't think it did, but I could have if we're just playing it and we only see the face of the machine.
So theoretically, the way in gambling you're supposed to navigate this problem, like for example, if you're playing poker and you know that most of the time, if you call this bet, you are going to win. The only way that most of the time, if you call the bet, you're going to win is if you incentivize him to bluff in certain situations, which means that sometimes you need to call. Even if you're like, most of the time, I'm probably going to lose this hand. So you have to have at least some element of randomness in your in the way that you approach this problem. So even if you know most of the time, taking in our example, it's gonna be lever two is gonna be the one for. You would want to have some way of telling the algorithm to randomly pick a different one. Sometimes, and the amount of time you would want to pick a different one should be somewhat proportional to how tight your automation is.
Yeah, but this comes back to the issue that is more like what Andy was talking about, like what are your actual goals, right? If I just say that our goal is to maximize the mean return, and one of those things is set up for these very rare but very, very lucrative events, and I stop that lever because, you know, it didn't look good for the samples that I drew, then I screwed myself. And obviously I'm never going to hit the rare
That's what I'm
event.
saying, you need to come back to those levers occasionally.
Yeah, that's all I'm saying. That's all I'm
Yeah,
saying.
I will.
That's all I'm saying. That's all I'm saying. Did you want to say something else?
No, I think you guys have.
Okay. All right. Let's go back. All right. So I guess we are mostly in agreement here that you actually should never completely give up on the arm. Now, I'm not saying you should play it just as if it was a outstanding performer like your best performing arm. I'm not saying that. Yeah, go ahead.
I'm sorry, with this, and this would all be with the assumption that this is maybe a real world problem where the decision space, the consequences within it are not completely predicted. Like in your program,
Mm-hmm.
there are arms where we could say, hey, if this returns less often for a less lucrative thing, yes, I should absolutely give up on it because that arm returns less frequently and less lucrative. Whereas in the real world, I might say, hey, I don't know he looked at your program apparently and said, hey, there's no secret $1 million return.
Mm-hmm.
There's nothing here.
Mm-hmm.
And so that decision space is fully solved. Now, in the real world, you might kind of be saying, okay, well, this didn't work in the past, but circumstances can continue to evolve. So I do need to kind of touch that every once in a while and check.
Yeah. It definitely, this is a property where environments are stochastic, right? Because if they're deterministic, you try a thing one time. You know, if you're playing chess and you play a move in a certain position, it's that chess game is going to play out like any other chess game where you try that move in that position. But anything that's random, and you know, many, but not all battlefield simulations these days, most of them I would say, have a stochastic element in them, and combat resolution or possibly other elements as well. So it is relevant. Okay. All right. So we'll play bad looking options less, sure, but we won't completely give up on them. All right. Well, all right, the algorithm's here. All right, so all right, since it gives you this this detail, let's look at this and we can go back in and see how a very simple reinforcement learning algorithm plays the game. So it's using the epsilon greedy strategy, which is a thing even for simple serious systems built with reinforcement learning these days. Epsilon greedy, absolutely a thing, but it's not the name of a reinforcement learning algorithm per se. Okay, this is just a reinforcement learning algorithm that uses this element. And what is the epsilon greedy element? Okay, you generate a random number, you have some small fixed epsilon, say 5%. I think maybe it's like 20% in that game. We'll get Nick to check the code later. So, all right. And so if you're under that 5%, 20%, whatever it is, threshold, okay, then what you do is you pull a randomly selected arm. Just a totally, so this is like in plain English, which is not good form for a technical lecture, right? But in plain English, when someone says randomly, I chose it randomly, usually they mean a uniform distribution over the options. Okay, and that is what I mean here. Use uniform distribution, and this is what makes you never completely give up on every arm. Because other than that, okay, this is what we call explore mode. This is going to make sure that we explore the space of our options adequately and never stop doing some amount of exploration. Okay, otherwise, and again, epsilon is meant to be small, so most of the time we're not going to be in explore mode, but rather in exploit mode. We're exploiting what? Exploiting our own knowledge about the properties of the arm, right? So what we'll do is we'll pull the arm with the highest expected return. Kind of makes sense? Yeah, if we go back to the thing, which by the way, the link is live, so you can go ahead and It's not just Nick, but you can all play with this if you want to. Again, if we go and click reinforcement learning here, okay, if it is in exploit mode, which arm is it going to pull?
The one with the highest PV.
Yes, which is 2. Okay, otherwise, uniform distribution over the rest. So let's go. So here you see epsilon is 0.2. The random number is under 0.2, so it's in explore mode. Okay, and we see it chose lever 3, despite the fact that lever 2 has a best return. Now, oh, look what happened. It also got hit in lever 3, and now these two are tied. So when we go back to exploit mode, I'm not sure. It's going to have to be a tie break. So let's try the next step. Okay, it's actually another explore, and it chose lever 1, and lever 1 flubbed it. Okay, let's go again. Okay, finally we get an exploit. And you see what happened. It went with, looks like it went with lever 2. Lever 2 failed. So now the next time we have an exploit, there's going to be a clear winner, right? 3 is going to be our choice for exploit. And there we go. Yeah. You kind of see how this is working? Okay, that's got like a lot of what makes reinforcement learning in it, with the exception of the fact that we don't have different situations. And our action space isn't very rich either. And in a real environment, you're going to have to actually look at what's going on, not just I'm standing here with the coin in my hand. That's always my situation. It's always the same, and therefore I can ignore it. But we'll get there by and by. So you can go in here and you can just go kind of see how it ends up playing. It looks like, look at this. Lever 3 looks like it's the choice of the reinforcement learner. You can decide if you agree with that. All right, good. All right. Okay. All right. So, right. So one of the things a reinforcement learning algorithm has to do is it has to solve this credit assignment problem. The principles there are the same as for the last slide. Now, one of the things is this is an explanation of why the slot machine problem is easy, okay? Which is that when we pull lever 2, if we're unhappy with what happened, we know to blame lever 2, okay? Whereas if you're playing chess and I make a move and okay, it just got really, really ugly when my opponent made that move. Was it my last move necessarily that got me to that pass? Maybe, maybe not. It could have been something I did 10 moves ago that was dumb. Okay? Especially when you're a beginner, you don't know that. You don't get that information for free. That's the credit assignment problem. In order to learn and to improve your behavior, if you can't solve the credit assignment problem successfully, then how do you learn from experience? It's pretty hard, right? Maybe impossible. Okay. So how are we going to see the credit assignment problem approached? Okay, it is a difficult problem, but we're going to approach it typically in 2 ways. One is that we tend to give recent actions more credit. Okay, now that's just a kind of that's a bias, but I think it's one we can all sympathize with. It's like all of the things being equal in my chess game. If I just made a move and just get a terrible counter, I lose a piece, or I get checkmated or something, right? All things being equal, you might think my last move is probably bad. Okay, maybe not, but all things being equal, I would think rather so. Okay, so that's this idea here, that we give recent actions more credit, but we don't just stop there. We average out random fluctuations. Well, what does that mean? Well, let's say my last move before I got checkmated was totally innocent. It was a totally legit move. Okay. But because of principle 1 here, I have the impression now that, moving the rook pawn, it's a bad idea. I got checkmated when I did that last time. Okay. Well, it's pretty benign, but in fact, maybe I got checkmated at least, I got checkmated once doing it. And because of this principle, I'm averse to doing that. Okay, that's fine. But remember, if in the context of a reinforcement learning system, am I never going to move a rook pawn again? Never going to make a move like it again? No, because we have to we don't ever give up on an action. So I might not touch it for a long time, but eventually I'm going to go and try it again. And if it's benign, then hopefully I'll see in the next time or the one after that, and I'll be able to average out the random fluctuation. The random fluctuation is the time I did it and I get checkmated. That was just bad luck. Okay. And hopefully I'll see, oh, most of the time it's totally fine to do that. Okay. On average, and therefore on average, it's fine. And that helps me solve my credit assignment problem. Does that make sense? All right. So we're going to get into the math shortly. And the math is meant to make things clear. And sometimes I find it has the opposite effect, where now stuff starts looking like magic. This is really all it's intended to go on in the math. All right, so utility-based learning, i.e. reinforcement learning. Those are going to be synonyms for us for a few lectures here. Okay, so the utility is one number that represents the total value of a particular action in a particular situation. Okay, it's a measure of total return, and reinforcement algorithms track that measure. Okay, now the typical way that return is written in a reinforcement learning textbook or algorithm description is as the Q function, Q of AS, where A is the action that I'm going to take in S, that specific situation. If I know Q of AS, that means I know, or I have an estimate of, the expected return in that situation. And you could say, well, if I had that function, if you just give me that function, I'm in a good situation to make good action choices. I'll just see what situation am I in, and I'll plug that there. I'll plug in all the different actions I think are reasonable into the first slot. I'll look for the biggest number, biggest return. Okay, so that's what we want to get to. Just to make the notation a little simpler, and like for problems like the credit assignment problem, where the situation really is always just one situation, so you might as well just drop that out. Okay, I'll just write this instead. Okay, this is just E as in expected value. U as in utility. Expected value utility. Hat as in it's an estimate, not an actual, not a value computed by first principles. Okay, good, fair enough. Yeah. All right. Right, so utility-based learning involves estimating the expected utility of all available actions in each possible situation. Okay, this enables the action with the greatest expected utility to be chosen. Yes, okay. All right. Right. So there's an issue of time here, right? So I like to say, I'll make you an offer. Don't trust me. I'll make you an offer. Yeah. You give me 15 bucks, I'll give you back 20 bucks. What could go wrong? What do you want to ask me back?
What are you doing with this 15 bucks?
Well, what's that?
What are you planning on doing?
That's not your business.
We went.
I'm spending it on important personal projects, I'll have you know. Now, the right answer is,
When?
yeah, when do I get my 20 bucks? And I say, oh, well, in 10 years. And they say, yeah, no thanks. I'll just drop it in my savings account and I'll do better than that, right? So that's how time factors in to rewards. And this is a model which works really, really well in the modern world with financial rewards. Okay, it works less well maybe with rewards on a battlefield, but it's the model that because it's just so easy to understand and it's intuitive and it makes general sense, it's adopted pretty much universally. Okay. All right. So what we're going to typically assume is that there's an exponential decay to the reward that you're going to get. Okay, and this again from a financial setting, it's dead obvious where this is from. Assuming that you're in a modern economy, and assuming you're not in the middle of a financial crisis, that assumes that if I say you're going to put that money out, you're going to invest it in like the best safe interest rate. That needs to mean something, right? An economy in crisis, that doesn't mean anything. Okay. But today you'd go off and you'd look for a money fund, or you'd look for something like that that has essentially zero risk, and look at what that return is. Okay. So, right. So let's go through this. So let's say, so $1,000 reward. If $1,000 comes in today, I'm saying it's worth more than $1,000 reward. Let's say 90 days into the future. Okay. How much more? Okay. Let's assume that a reward received today, if I got the reward today, I could invest it. And what I would get from this safe fund, it would give me a return, I'm saying per day. It's not usually what your bank is going to cite you. It'll be probably per year. Okay. But a reward per day of P, right? That's a percentage. Okay. So, reward per day, I have no idea. Like right now, safe money gets laid what, like 4% a year, but it's 4% divided by 356 days in the year. So it's a pretty small number. So it's 4 over 400, pretty small. Okay. But whatever that number is, that's what your P is. Okay. So if I take my D dollars that you give me today and I put it for 90 days at an interest rate, a return rate of P, right? So now I get one plus P raised to the 90, right? You've seen this math many times, I'm sure. And if you haven't, it should still make sense to you. Like if P is 0, this will just be 1. It just says that your money doesn't change, right? In fact, I expect to get more money. So 1 plus P should make some sense, raised to the 90. Okay. Now, on the other hand, if I invert that math, what it tells me is that if I say, oh, did you think you were going to get your $1,000 today? No, you're going to get it in 90 days. Okay, well, then you got to invert that math and you do 1,000 divided by 1 plus P to the 90. Okay, and that's where you get your exponential fall off in value as a function of the number of days, the time. Here, let's look. Okay, does that make sense? All right. The way it looks more typically is, so we talk about rewards R that are going to be intermittently be given to our reinforcement learning system. It could be all the time. It could be a constant stream of rewards. They could be super, super rare, right? So, more rewards more often is usually better than fewer rewards, right? So it's better when you're playing chess to learn if you've got, if you've got your older brother standing next to you who's like makes a funny face when you go try to touch it. It's like, oh, okay, you don't want to move that piece. Okay, you're getting some kind of rewards in process. If you don't have older brother around and you're a new chess player, you don't know anything till you get to the very end. It's like, oh, you just lost. Okay, so all right. So we assume we're going to get a reward R. We don't know how often, but in general, we're going to have to wait to get the next reward. So it's going to come at a time T into the future. And we will say that we're going to discount it by lambda to the T, where lambda is some number that an appropriate number less than 1. Okay. So in the example above, lambda would be 1 over 1 plus P, right? It's really less than 1. Good. Okay, that's the model that we use in reinforcement learning. And again, it makes beautiful sense for financial applications, which, by the way, they use reinforcement learning to death in financial applications. But it's not terrible anywhere, I guess. That's why it's been adopted. Okay, now this kind of squishy thing where the rewards are kind of going down in value all the time, and they are going down at depending on this rate. Lambda is maybe something that some of you haven't thought about a lot, but if you're a physicist, since I had my early training in physics, physicists know how to think about this because they're dealing with this all the time in the context of radioactive materials, right? So you have all kinds of radioactive materials, some which stay radioactive for like a minute after you do an experiment with them, and you're basically back to normal, and other ones that'll take hundreds of years for them to get back to normal. So it's very important that they understand this very well. And the way they talk about it is with this notion of a half-life. And the half-life is just if you have any kind of process where a quantity is decreasing over time, the half-life is, well, how much time does it take for you to lose half of what you started with? So the math is pretty easy. So you could take any lambda, and if you're trying to understand it in terms of half-life, you say, well, what is the amount of time such that when I raise lambda to that quantity, I get 0.5, because that means I lost half of my initial value. Okay, which means that the half-life, just solving this by taking logs on both sides, the half-life is the log of 0.5 divided by the log of lambda. Okay, and you can just kind of see over here how this plays out. So if you have a very small lambda, your value goes away instantly, pretty much. Okay, if you have a very large one, it can take a long time for it to go away, and the half-life can be anything, any number between greater than 0 and less than, greater than 0 and all the way up to infinity. It's unbounded. Yeah, good. I don't know if this helps you or not. It kind of helps me, because I don't know. I think the half-lives are more intuitive to talk about lambdas. But so what we typically do in reinforcement learning is somebody, whoever sets the problem up first, tries to figure out what kind of lambda makes sense. So let's say, you're doing ground combat, and you're tactical ground combat, and you start thinking about, when I get an advantage, like I seize a piece of terrain, or I do a great job at attriting the enemy with few losses. Like, how durable is that, right? You can think about that. It's not going to last 100 years, that advantage, I can tell you that. And it's going to last more than 10 minutes, I can tell you that. So you're going to have to decide somewhere in the middle range that, okay, we'll say, at about this amount of time, and in about half a day, that value goes down to about half or whatever. That's for an expert in the domain to make the judgment, not me, okay? So, and this is the kind of way you could be thinking about that. So the way it works is then you would do that and you would say, okay, for this application, a lambda of 0.85 is the most appropriate. And then I would say, oh, 0.85, okay. And then from the rest of the time out, I won't think about lambda. It'll just be a parameter of my problem. And I'll just do my best to try to maximize assuming a lambda of 0.8. Okay, so yeah.
Are there targets for where, like, standardized targets for how close to 0 you would be trying to get, like half-life? This is a terrible way of me explaining the problem, but a half-life of 1, you're at 50%, half-life of 2, you're down to 25%, half-life of 3, you're down to 12.5%. Are people trying to get like below 5% or below 1%?
I don't, so
in terms of
I'm not tracking, right? So the half-life is telling you how long. Again, think about tactics. Like, how long you pull off something really good, like how durable is that going to be? How about how much time goes by before you've lost half of that? You lose that time goes by again, you've now lost 3/4 of that, and so forth. That's kind of the model. Okay. All right. Okay. All right. So to actually do some math, so like this is something you actually need to code up, though. Again, as with most algorithms in this course, I'm not going to ask you to code it up, but you will probably be using some software that's using this math under the hood. So I would want you to at least have thought about it. Okay. Now, it won't exactly be this math. This is like a little bit simplified, and also is a little bit more accurate, actually, than you're likely to actually see in a reinforcement learning package. I wouldn't see the need to be track quite so much information and be quite so accurate to the discounting model. Okay. All right, so let's go. So let's assume we have done the action. We took the action one time at time lowercase t. Okay, and then at time, this is a tau, that's the time at which we received a reward of lowercase r. Okay, and we're trying to compute the expected utility of that action. Okay, so the first thing to say is the nominal case, where I get the reward after I take the action. That's the normal case, right? So in that case, the expected return is just the reward discounted by the amount of time that elapsed between when I took the action and when I took the reward. So pretty intuitive. Okay, if it's the other way around and the reward came in at the same time or maybe even before the action, then my claim is we have no information about the expected reward. Does that make sense? Yeah. Well, how would we? I mean, you might, again, in stochastic environments, you might get lucky to get a reward for nothing. But that clearly doesn't have anything to do with the action that wasn't taken. Right? We assume normal causality and normal physics apply here. No, I take an action now, and in 1800 something happens. Okay, yeah, that's great science fiction, but not very practical. Okay, now you'll notice that despite that I say we have no information, you'll see I represent that as kind of a value of 0, which is a little bit, iffy, but if you have to give it I needed to give it a specific value for these equations, so I think that's not a bad choice. But let's say it's as good as any other choice. Maybe it isn't a great choice. All right, now in order to write one equation that handles both cases, because this is going to get more complicated in a moment in the next slide or two, okay, I introduced this h function here. So this is a function called the Heaviside function. I don't know if you've ever seen this before. So this is a function where if the argument is greater than 0, it is 1. And if it's 0 or less than 0, it is 0. Okay. So this is like I say. So if it's the normal case that I took the action today and I get the reward in 2 days, this will be positive. This h just becomes a 1. Okay, and then this is exactly what we would expect. But if it's the case that no, I randomly got a reward out of nowhere on Monday, I didn't take the action till Tuesday, okay, in that case, this becomes 0, and it says, well, your expected utility, you should estimate that as 0. So that assumes 0 is a neutral value. It isn't in all domains. It isn't in all domains. Sometimes things are steadily getting worse if you don't do anything, and so a neutral value might be a negative value. Or sometimes you're getting benefit even when you don't do anything, and then a neutral value might be a positive value. But all things being equal, not a terrible choice, and it lets me give you one equation for each one of these cases instead of 2 or more equations. Are we good with that? Okay. So now I can easily extend that and say, okay, yeah, you got that first reward, but now you get a second, third, fourth reward. Okay. How would you extend that math? What you do is you would now sum a term like this over each reward that you got. Okay, now again, you took the action only once, so there's one lowercase t, but you're getting successive rewards at different times, tau. Okay, and then we have the equation here. Again, also the magnitude of the reward is different each time. Again, we're trying to write a general equation here. So this will be fine. It should work fine. It will zero out any rewards that came before the time we took our action. And other than that, what we'll have here is just a net return from that one action. And I hope it makes sense to you that it's the net return, right? That's what we care about, right? I care about how many goodies did you get in total for taking that one action? It doesn't make too much difference to me whether you get it all in one fell swoop, your reward all in one fell swoop, or because you did something good, Monday, Tuesday, Wednesday, Thursday, you get rewarded each day because you did something so great. Yeah, I just care about the net. Awesome. Okay, that's the simplest version. It's a little more complicated, but okay. All right, so I think this might be the more complicated version. So this just assumes the only difference here is now this is an action you take periodically. You've taken it periodically, not just one time. Okay, so now I'm going to have to do a double sum down here, okay, where one of the sums is for the rewards. That's the sum that was on the last slide, and the other one is indexing the different tries of the action. Okay, and what we're going to do is so imagine now I'm taking this action periodically, here and here, and I'm getting rewards, boom, 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 boom. Okay, now it becomes ambiguous, especially for the rewards that come after the second try of the action. Are those rewards from that most proximate try, or are they from the earlier try? Okay, there's no right answer for that. You kind of have to know. I mean, maybe in a particular environment. What I mean by no right answer is there's no general answer. It will depend on your environment. So I think the typical way of dealing with that is actually just essentially to separately
treat each one of the action tries as if it's the only action try. And do the math based on that, the math on the last slide. And then average over that expected return and say that's the expected return per action try. Make sense? The words, yeah, should at least make sense, even if it doesn't look perfect. And if you look at the equation enough, it should start to look perfect. Okay, so right, so we're just averaging. That's this, right? This is the averaging going on here. N tries 1 over n. This is the equation from last time, but now each time we use that equation, it's for a specific time where we tried the action. Yeah. Okay.
All right. Now, what we can do is let's see if we really understand it. Okay.
Let's, you guys can look at the last slide and keep me honest here. I'll see if we can solve a few of these, and then there's a few more I might want to cry and groan or before the time or whatever. All right, so lambda is 0.9. We tried the action at 23.4, and we previously received a utility of 10 at time 10.1. What is the expected utility? So it's not till time 23.2 that we try the action, but before that, we received our reward, which I'm calling utility here. So what's the expected utility in that case? What does that equation tell us? It's 0. It says it's 0. Again, debatable choice. Okay, that's the only debatable aspect, I think, of the whole thing, but it is a debatable choice. That's what it says. So yeah, that's our answer. All right. Next, let's see this one.
So long.
All right. All right. So now we're going to try action at 23.4 and receive a utility of 10 at a later time. Okay. So hopefully we know how to do that. So the way we're going to estimate utility is, okay, it's going to be the reward, right? Which is 10, right? 10 times our lambda, which is 0.9, raised to the power of the amount of time that elapses in between. So that would be 31.2 minus 22.4, right? That's all the exponent. That make sense? Yeah. All right. And then the next one says that, okay, now what happens if, again, see, this is kind of a continuing example. What happens if, in addition, you also receive a utility of 50 at a later time? Okay, then we would have it be, again, we sum up those utilities, right? So we're going to have this, same as what we had. Okay, plus, so utility is a much bigger utility in base, but we had to wait longer to get it. So now we still tried the action at 23.4, right? We had to wait much longer to get it. Probably, probably it's a bad deal for the impact on the sum. Right, because messing with this is very sensitive to changes in the exponent. That's where we get the exponential decay. But there it is. And you do the math with the calculator and see how much each one impacts. Okay, and then the last thing, and then we'll be done for today, is try action. Okay, so this time we're going to try the action 2 different times. Okay, now remember, what you do is you consider each one of those independently and average them. Right, that's what that equation says to do. Okay, so okay, so it's going to be 1/2, and then I'm going to have 2 terms here. The other term, right? First one will be for the first action, the next one for the second action. Okay, so the first one, we tried the action 23.4. Okay, utility of 5 received at time 9.6. I could ignore that. That contribution is going to be 0. That's what that H function will tell you. Okay, so 23 at time, is that the same? Geez, I changed it a little bit. All right, that's fine. Let's go. I'll just write fast. Okay, 23 times 0.9 raised to the, okay, 34.3 is when we got the reward, minus when we took the action. Again, we're just concerned with the first action trial. Okay, and then I gotta have a term for each one of these, 67. Okay, I received a 51.2 minus 23.4 plus. The last one is 20 at a much later time.
101.5.
Thank you, 101.5 minus 23.4. Okay, so that's the first term. Brace. Okay, second term. Okay, the second trial didn't happen to 49.5. So this one is not going to affect, it. The H function will zero it out. This one will also be zeroed out. This one will not. The last two will not. So we've got to put those into the computation. Okay, so 67, 0.9, 51.2, and the trial time is 49.5 in this case. Okay, and then 20 at 0.9 to the 101.5 minus 49.5. Cool. Okay, fair enough. Questions about that? So you should definitely maybe try this on your own, maybe looking at the equation. And then there are some more, a different type of problem that's also in the notes. Make sure if you can. All right. All right, done for today. Yes.